Welcome to the course module of communication engineering. So in the last lecture, we have seen the delta modulation. Okay. In the delta modulation, we have seen the basic steps that we need to produce a delta modulated output. And we already seen the related problems like what is slope overload and what is granular noise. So in the last lecture, I haven't shown you this particular picture, okay, regarding the adaptive delta modulation. So please let's see this particular picture, okay, that will give you an idea. So how this adaptive delta modulation is actually performed. So basically in the case of delta modulation, I said that in the linear delta modulation, the step size that we choose is generally a constant, okay. It is not varying with respect to the slope of our message signal. So that's lead to actually to have the slope overload conditions or granular noise. So in the case of adaptive delta modulation, what we can have is this step size. Okay, here we can see that the output that our delta modulator is going to produce based on the error signal, that will be a variable in nature. Okay, its step size will be variable in nature. So it will be depending on the basically slope of our message signal. So here we can see that in this range, the signal is actually having a steep change in it. Okay. So at this point, the slope of this particular message signal is high. Okay. And therefore, to accommodate this steep change in the message signal, the step size of this delta modulator is also large. Okay, is also large. Here we can see that its step size is large. Okay, so here we have the very large step size to accommodate this steep change in the message signal. Similarly, wherever the like variation in the message signal is small, here we can find that it is having a very small variations. At this time, to accommodate or to track this small variations properly, the step size is actually reduced. Okay, it is reduced at this point. So this way, basically, we have in the adaptive delta modulation a particular block that will be able to control the size of our steps that we are going to use based on the slope of the message signal. So this is all about delta modulation and adaptive delta modulation. So here I'm not going to discuss more about the adaptive delta modulation. This much for the present discussion is enough. Okay, this much discussion is enough for the present scenario. So today I'm going to discuss about one more topic, which is very important topic. Okay, which is time division multiplexing. So now you try to see what is this time division multiplexing scheme and how it is actually implemented in real life. So you try to understand in one of the practical situation. Okay, first you try to assume one of the practical situations. Let us suppose that while you are watching this particular video, there may be a millions of subscribers or users are actually maybe talking over the phone. So if you see how these two peoples are actually connecting, okay, if it is a wireless media, we know that the signal is actually transmitted through the wireless channel, and then they are going to be connected. Okay, if suppose that if it is a like wired media, if you take the example of the wired media, then if suppose there are millions of subscribers are talking over the phone, then how many such like wired dedicated line has to be laid down to have the proper connection between the two users. Suppose that one user at this end and another user at the other end. Okay, then how many such subscriber lines that we need to have so that a connection can be established and then two people can talk to each other. So obviously, if we say that there are million subscribers, then it doesn't mean that we need to have the million subscriber lines. Okay, we cannot have the million subscriber lines, so we cannot let down the millions copper cables or optical fiber cables to have the connection between two persons. Okay, we cannot have, because we cannot afford so much of cost, because laying down any transmission lines, okay, is a costly thing. Okay, it is a man-made media, and therefore we need to have a we have to invest in materials. Okay, so laying down so much of cables are not possible. So we cannot have a dedicated line that will be used for a particular two people. Okay, one at the transmitter end and other is at the receiving end. Okay, we cannot have a dedicated line for them. So generally what we perform is we are having the limited number of transmission lines. Okay, we are having just limited number of transmission lines, and then the same transmission lines are actually used for making this all calls how that means to connect two people from the two different places by having just this limited number of transmission lines. Okay, so how it may be performed, okay, how it can be performed, that we have to look at, and that you can get certain idea about how it is done by studying this time division multiplexing. So let's try to see this. Okay, because we cannot have the millions number of transmission line, we are having just a limited number of transmission lines. Then how this limited lines are going to accommodate a million number of subscribers? Okay, how million number of people can talk over the phone, okay, simultaneously, how they can talk? And sometimes you may be finding that when you are calling someone, you maybe get a message that the line is busy. Okay, the line is busy. So how this line is busy? Because we are having the finite number of transmission lines, and now those all lines are actually being occupied, and now you cannot have any free media available that can send your particular signal, and therefore you will get a this message that the line is busy. Okay, so try to understand this, how it is actually being implemented in real life. So you try to see this particular block diagram of a time division multiplexing system. Okay, so we have already seen that in the case of analog message signal, if we want to send the analog message signal into a digital form, okay, first we need to pass the message signal through a low pass filter, which is also called as the anti-aliasing filters. Okay, just to remove the high frequency component. You remember that this anti-aliasing filter or a low pass filter, the function is again to band limit the message signal. Okay, so let us say that we are having total n number of such users. Okay, we are having total n number of such users that want to send their information to the n other users at the other end. Okay, so this is the n number of messages that we want to send. So first we need to band limit this signal, and after having this band limiting process, okay, as we already seen in the case of pulse code modulation, what we perform is we have to go for the sampling, and after the sampling we have to go for the quantization encoding, and then this encoded signal has to be sent through the transmission channel. So here we can see that if you we have already seen the basic mechanism of sampling. Okay, we have already seen there should be a Nyquist criteria that we need to follow for transmission of a particular signal. So if we have to follow the transmission means this sampling criteria, so based on the Nyquist theorem, the sampling frequency should be equal to or greater than twice of the maximum message signal frequency. So that criteria we need to follow, so that from the sampled version of the signal, the reconstruction of the message signal may be possible at the receiver end. Otherwise, it is not possible. So what generally we do, if you see, let us suppose that we have a particular message signal M1T, okay. Then if we talk about the sampling of this message signal M1T, then let us say the sampling interval is equals to TS, okay. So at every TS second, which is following the Nyquist criteria, okay. So at every TS second, we are going to take the sample of message M1T. So at a regular interval of time TS, we are going to take the samples of our message signal M1T. So here you can see that between the two consecutive samples, okay, the first sample of the message M1T we have taken at this particular point, okay, and then the next sample is actually being taken after TS second, okay. So at this point we are going to take the message signal. So now what we can see from this thing is that In between TS second, okay, the system is idle and it is not taking any other samples. Okay, so basically between these two samples, okay, between these two consecutive samples, no sample is being actually transmitted. Okay, so the same concept what we have done is because within this time TS, no samples are being sent. So what we thought is, if we can have the samples of some other message signal that can be interleaved or it can be interlaced in between these two samples is possible, then we can obviously means we can obviously save our time and bandwidth requirement of transmission of the message signals. Okay, so generally what we can have is, because in between these two samples, what we can have is we can have the sample of some other message signal M2 also. Okay, so it is not just only one message signal, we can take several message signals, okay, whose samples can be accommodated between the two samples of our message signal M1T. Okay, so here we can see, just for the sake of simplicity, we have just taken the two message signal M1T and M2T, and here we are actually showing how these two signals can be interleaved or interlaced. Okay, so basically here we can see that first we have taken the sample of message M1T, and after a certain amount of time the next sample is to be taken from the message signal M2T. Then again the next time we are going to take the sample of the message signal M1T here. Okay, and then again the sample that we have to take is from the message signal M2T. Okay, so you remember that in between in M1T, if you see that at the regular interval of spacing like TS, okay, we are repeatedly taking the samples of our message signal M1T. And similarly for M2T is also, this TS is actually a constant. Okay, in between the two samples, this sampling interval is a constant, and we are also sending the samples of our message signal M2T. So what we are trying to do is between these two samples, we are trying to interleave a number of samples of different message signals. Okay, so how it is actually implemented in real life, we can see that first we have to take the message signal, then we have to band limit the message signal, and then this message signal has to be connected through a commutator circuit. Okay, remember that this is our mechanical rotatory switch. Okay, so here it is having a certain poles, okay, through which this signals is should be connected. Okay, there should be certain poles. So here we have a certain poles, and there will be a rotatory switch. Okay, and this rotatory switch is going to be rotated at a certain frequency. Okay, it will be rotated at a certain frequency. So at this commutator, what this is going to do is, once this switch is rotated and it will be connected to this pole, then this is going to be sampled. This passive signal 1 is going to be sampled once this rotatory switch is actually making a contact with this particular pole. So this will be sampled, and then this sampled signal is going to be used for the pulse modulation. Okay, so here we can have a different pulse modulation scheme, like maybe PCM, like pulse modulation directly. Okay, it may be PWM, PPM, whatever. Okay, so let us suppose that if we are going to for the PCM system, okay, then it is going to have this and then it is modulating a pulse. Okay, pulse modulator will be there, and then based on the modulation scheme, quantization or encoding process may be done, and then again this communication channel, within this communication channel the encoded signal will be sent. Okay, and then again a pulse demodulator will be there. Okay, and then again a clock's pulses will be applied here. Okay, so again it will be demodulated, and then here it has to be should be connected to a proper output. Okay, so let us say that suppose if we want to connect this message signal one to this particular output, okay, from this particular output. Okay, so what we try to do is we want to actually connect this particular subscriber which is at message number input, message input equals to 1. Okay, whatever be the subscriber at this point that we want to connect to this particular subscriber. Okay, where it is written equals to 1. So here once it is connected, okay, this has to be first sampled, and then all other means modulation processes will be done. Okay, and after doing this modulation, okay, this has to be sent through the channel. Okay, so here you can see that basically when it is rotated, this particular means rotatory switch is rotated at a certain frequency, you will find that at a regular interval of time, it is actually taking the samples from all other message signals. For example, first it is connected to message input 1, then it is connected to 2, then 3, 4, and so on. So it will be keep on taking the samples from each and every message input signals, okay, at a regular interval of time. And those message signals, okay, which are actually getting sampled is now getting encoded, okay, or quantized based on the modulation scheme, and then it will be sent to the other end. So if you see that at a one time, only one signal from one particular message input is actually being sent. Okay. So you remember that we are not actually sending all the signals together. You remember we are not sending all the signals together, but rather one by one signals are actually being sent. Okay. So first this signal is being sent, and then this commutator switch will be again connected to this point. Okay. So that time only this message signal will be sent. Okay, and this will be not connected here. Okay, so here we can understand that even if we have connected to a particular subscriber line, and if you are talking over the phone, you remember that you will be getting connected and disconnected for a small amount of time that you are not able to sense. Okay, we are not actually able to sense it, that we are going to means we are actually connecting and disconnecting at a regular interval of time. So here it is actually connecting, and then it is sending this particular information. Okay, so because this has to be connected to this line, there will be another decommutated circuit. Okay, so this will be first received, and then it will be demodulated. Okay, it will be demodulated, and then the same sample signal has to be generated. Okay, or you can say that same analog signal has to be generated. Okay, so that signals is being actually generated at this point, and then after the demodulation process, you remember that after the demodulation process, and then there will be a decommutator switch. Okay, this function is similar to our commutator switch. Again, it is a rotatory switch. Okay, so when it is rotating here, it is anti-clockwise. Here you can see that it is rotating clockwise. Okay, and these two switches should be synchronized. Okay, it should be in synchronism, so that this switches may be able to know that at what point of time which particular sample has to be sent to which particular output. Okay, for example, once we have sent this particular sample number 1, okay, from the message input 1. Okay, so from the first message M1, if we have sampled this signal, when it is being transmitted through the transmitter, the decommutator should able to know that this signal has to be sent to this particular output pin number 1. Okay, so it has to be provided to this particular pin number 1. So that should be done by having the synchronization between these two commutator and the decommutator at the receiving end. So that has to be implemented by a certain synchronism mechanisms. Okay, how to synchronize the two things, right? So to have that idea, if you understood how actually it works, okay, so whatever I said, that you can see that even we are having just a single dedicated line. Okay, we are just having a single transmission line. Okay, in between the transmitter and the receiver, but you must be able to follow that there are large number of like subscribers are actually connected at the two ends. Okay, even at the transmitter end and at the receiver end, a large number of subscribers are actually being connected, but in between we are just having a single transmission line. And because of this type of nature of transmission, okay, in which all the messages actually have their individual time slots for transmission, and therefore they will get their opportunity in after every TS seconds, and thereby actually they are actually sending their signals in every TS regular means TS seconds, and the same signal is being received at the other end. Okay, and then it is connecting disconnecting for every TS second, and we are not able to sense it. So this way a single dedicated line can be used for transmission of the so many of the message signals. Okay, so now let us try to assume that the number of channel, you can say, or the number of messages signals that we want to time division multiplex. Okay, let us say it is a capital N. If it is a number of signals or number of channels, you can say, or number of signals that you can say that you want to multiplex this capital N, and let us say that this sampling interval that we have taken, okay, the sampling interval between the two samples of same message signal is equals to TS. So remember that this is not our sampling interval. It will be the interval in which this commutator will make one rotation. Okay, so once it is connected at this point, okay, again after TS second, it will be again connected to this point only. Okay, so this will be our sampling interval. Fine. So let us suppose that the sampling frequency is equals to Fs. So it is having its sampling interval equals to Ts second. That will be equals to 1 upon Fs. So now let us say if we want to use here the pulse code modulation system, okay. So that time what we can have is we have to quantize it. Okay, here these things you can change. Okay, here like it has been shown like we are having a pulse modulator. Okay, so we can change it and we can have a pulse coded modulation system. Okay, so we can have the PCM system over here. Okay, so just for the sake of simplicity, it has shown like pulse modulator. Okay, based on the magnitude of the sampled signal, the pulse of the message, this particular pulses is going to be decided. But here we can have the PCM system also. So for example, if we are having a PCM system, you know that we will be having a quantizer followed by a particular encoder. Okay, so let's say that this each sample from each message signal is being actually encoded by having the small n number of bits. Okay, small n number of bits. Then what we can have is we can calculate what will be the bit duration, because the basic important parameter is what will be the bit rate that we can obtain by multiplexing the capital N number of message signals. So basically what we have to see is that, let us suppose that we are having n equals to 4, means the each sample is going to be encoded by 4 bits. Okay, by encoded by 4 bits, because we might have taken this the number of quantization level is equals to 16. So 2 to the power 4 is giving you 16. So if we are having 16 quantization level, obviously the number of bits required for encoding is equals to 4. So let us suppose the number of bits are equals to 4, and there are total 5 number of such signals we want to multiplex. So we can see that within the TS duration, okay, within the TS duration, we are going to take the total 5 samples. Okay, each from each particular message signal. Okay, because we are having total 5 signals, we are going to take 5 samples, and each sample is going to be encoded by 4 bits. So it means that within this TS duration, okay, within this TS duration, that we can we can call it as a frame. Okay, one frame. Okay, so within this one frame, how many bits we are actually transmitted? So we are transmitting total 20 bits. We can see that this 1001 is corresponding to message signal 1, and this 0011 is corresponding to message signal 2, and this is for 3, this is for 4, and this is for 5. So basically total 5 samples is being actually encoded, and then these many of bits that we are going to transmit within the TS second. So as we know that within this TS second, these many bits we are actually transmitting, then we can calculate what will be the bit duration. Okay, I have already explained you that all the bits has to be further we have to use the line codings. Okay, we have to further use the line coding before sending to this or for sending through the channels. Okay, so to calculate this bit duration TB, this can be calculated within the TS second. We are sending the total number of bits. Okay, so this TS divided by total number of bits. So this total number of bits will be small n multiplied with the capital N. So where small n denotes the number of bits each sample. Okay, and the capital N denotes the number of message signal that we want to multiplex. So this way we can actually calculate the bit rate, and as we know that the bit rate is actually related to its means bit duration is related to its bit rate. So RB is equals to 1 upon TB. Now you can think of if as I said that this commutator and this decommutator should be synchronized. So generally what happens is to achieve this synchronization, okay, to achieve this synchronization of the commutator and decommutator, what we perform is we generally add some extra bit at the end of the each frame. So let us suppose this was the frame, okay, we could have added a certain number of bits at the end of the frame. Once this particular bit like appears, okay, this bit pattern is appears, then the decommutator will automatically know that it is the end of the frame and the next frame is going to appear, okay. And this way it may be able to make the synchronism or establish a synchronism between the commutator and the decommutator. So certain synchronization bit may be added at the end of the frame. The synchronization bit may be also added even after each samples. Okay, there may be a mechanism in which we can add the extra number of synchronization bits at even each of the samples. Okay, so this is the 1001. So let us suppose this is the two 4 bits that we are using to represent the samples. Even after this, we can have one extra bit that may be used for the purpose of the synchronization. So you remember that whatever be the synchronism mechanism, whatever the way we have added the extra synchronization bit, then you remember within the TS second, all those bit has to be sent, okay, has to be sent. So along with all the encoded bits plus the synchronization bit has to be sent within the TS second. And that time, the bit duration that we are going to get TB, that will be equals to TS divided by NN plus A, where N is the number of synchronization bit. So you remember that whenever in the question, if this synchronization bit come, okay, then you, if it is given like it is added per frame, then this has to be considered as a frame, okay. If it is given like it is added per samples, then you have to calculate how many synchronization bit will be added in per frame, okay, if it is given as a per sample, okay. So how many samples we are taking, accordingly you have to calculate the number of synchronization bit in the per frame, and that way you can calculate the bit duration, and from bit duration you can automatically calculate the bit rate of this particular TDM system. Now you try to see one more thing about this time division multiplexing. This is very interesting. Okay, so let us suppose that if we have two message signals, okay, let us say it is two voice signals that we want to send, okay, M1T and M2T. Okay, let us say it is any arbitrary two signals M1T and M2T that we want to send, and assume that this message signal M1T is having its maximum frequency component is equals to 1 kilohertz. Okay, and this message signal M2T is actually having its maximum frequency component equals to 2 kilohertz. So now if we want to multiplex these two signals together and then we want to send it through the same channel, okay, a single channel, okay, then let us say that we want to calculate what will be the bit rate requirement for this particular case. So let's see, in the previous case, I told you that this commutator has to be rotated at a certain frequency, okay? And this has to be following the Nyquist criteria for each and every message signal. So if suppose that all the message signals that we want to multiplex are having the same number of, means is having the same maximum frequency component, okay? Let us say if it is all is having like 2 kilohertz, okay, having 2 kilohertz, then at that time what we can have is because all the maximum frequency component for all the message signals are equals to 2 kilohertz, we can choose this sampling frequency, minimum sampling frequency equals to 4 kilohertz, which is our Nyquist criteria, okay, 4 kilohertz. And that time each message signal is going to be sampled at its respective Nyquist rate, okay. So that time this sampling frequency can be equals to 4 kilohertz. But now when this is the situation, when M1T is equals to 1 kilohertz and M2T equals to 2 kilohertz, then we have to think of what should be the sampling frequency, because both the two message signals are having two different maximum frequency component. So if you go for this M1T, then you can find that it is having 1 kilohertz. So corresponding Nyquist frequency will be equals to 2 kilohertz. But if this commutator is rotating with 2 kilohertz sampling frequency, okay, then you can see here that this M2T is having its Nyquist frequency equals to 4 kilohertz. It means that when this sampling frequency here for the commutator, if we are taking equals to 2 kilohertz, this signal M2T is going to be undersampled. Okay, it is not following the Nyquist theorem. Okay, Nyquist criteria. So to get this frequency, okay, to sample this particular massive signal M2T, at least the sampling frequency should be equals to 4 kilohertz. Okay, so once we have the 4 kilohertz, then only this is going to be sample at its respective Nyquist rate. But if we choose this sampling frequency equals to 4 kilohertz, you can see that this signal M1T is getting oversampled. Okay, it is getting oversampled. So oversampling is not a problem. You remember that even if you do this oversampling doesn't make any difference. Okay, so it is not a problem. We will be able to reconstruct back the original massive signal. But undersampling we cannot perform, because once we do the undersampling, the same massive signal cannot be recovered back from its sampled version. So in this particular configuration, okay, if the way we have shown the massive signals are actually connected to this commutator, okay, if this is the configuration, then we can see that the sampling frequency cannot be 2 kilohertz, but the sampling frequency that we have to choose in this particular configuration is equals to 4 kilohertz. Okay, so once we take this 4 kilohertz, then let us suppose that the number of bits required is n equals to 10. Okay, and the capital N, it means the number of massive signal that we want to multiplex is equals to 2. So we can calculate the bit rate RB, that is equals to 1 upon TB. So that can be calculated as N multiplied with capital N divided by TS. Here I am not assuming that any synchronization bit is being added. Okay, so let us say it is N capital N divided by TS. So this can be further written as N into N multiplied with the sampling frequency Fs. So let us say we have already established that we have to take the Fs equals to 4 kilohertz. So if you substitute all these numbers, you will get the bit rate equals to 80 kbps, okay, kilobits per second. Now you try to just analyze the same problem in with another angle. Okay, so let us suppose we have the same massive signal M1T, which is having its frequency equals to 1 kilohertz. Okay, and another massive signal M2T, which is having its maximum frequency equals to 2 kilohertz. Now instead of connecting the massive signal M1T only once to this commutator, if we can have this type of configuration in which this massive signal M2T is actually being connected twice to this particular commutator. So you remember that there will be a certain poles at this points, okay, and we have to make a connection, okay. So this way, if we have connected this signal M2T twice, okay, to this particular poles, and now let us say this sampling frequency, okay, if sampling frequency, if we choose corresponding to 1 kilohertz. Okay, so 1 kilohertz, due to this 1 kilohertz, the Nyquist frequency that will be required is equals to 2 kilohertz. So let us say if it is rotating at the speed of 2 kilohertz. Okay, so what we can have is we can going to take means 2000 samples from this particular pole. Okay, because it is connected only once, so we are going to get 2000 samples per unit time. But here you can see that another 2000 sample we are going to take from this, and another 2000 we are going to take from this. It means that for the massive signal M2T, we are going to take 4000 samples per unit time, because it is connected twice in this particular configuration. Okay, so in this way we are going to collect 4000 samples from the massive signals M2T, okay, per unit time, and here we are going to collect the 2000 samples per unit time from this particular massive signal M1T. So you remember due to the change in this configuration, okay, the way we have connected this massive signal M2T to this particular commutator, just by having the sampling frequency even equals to Fs, okay, it is even equals to 2 kilohertz, we are able to sample the massive signal M2T at its respective Nyquist frequency, that is equals to 4 kilohertz. Okay, so if here if we take Fs equals to 2 kilohertz, you see that our massive signal is M1T is also going to be sampled at its respective Nyquist frequency, and M2T is also going to be sampled at its Nyquist frequency. And therefore here the sampling frequency in this particular configuration that we can take is equals to 2 kilohertz. Okay, so now you try to substitute the same thing, but you remember that in the previous case, okay, how many poles that we have used? We have used just 2 poles, and therefore capital N was equals to 2. Now here the number of poles that we have used is 1, 2, and 3, and therefore the capital N will be equals to 3. Okay, and the small n representing the number of bits used for encoding the each samples. So n equals to 10. So what we can have is we can again calculate the bit rate, and here the sampling frequency we have to choose equals to 2 kilohertz. So here it is 2 kilohertz, and it is the number of capital N is equals to 3. It is 10. So this bit rate that we are going to achieve is equals to 60 kbps. Now you you compare this to configuration. Okay, you try to compare this to configuration. You can find that in the first scheme, okay, the bit rate requirement is large. Okay, it is large. But in the case of second scheme, the bit rate requirement is actually 60 kbps. So often in the problems, if it is asked that what is the minimum bit rate required for this particular TDM, okay, then you have to just realize this configuration. Okay, there may be a large number of signals may be given, okay, and then it may have the same sampling frequency, it may have the same maximum frequency component, or it may be a different sampling frequency component, means maximum frequency component. And that time, based on the statement, if it is asking you that you realize a TDM system in which each message signal is going to be sampled at its respective Nyquist frequency, then you have to go for this particular configuration. Even if it is asking you to find out what will the minimum bit rate required for transmission of this time division multiplex signal, then again you have to go for this configuration, because this configuration is actually giving you a large amount of bit rate. Okay, the bit rate will be higher in this particular configuration. So you based on the statement, okay, if this figure is not given, okay, the based on the statement you have to select that which particular configuration we have to use for solving the problem. So you remember that this will be beneficial because the bit rate requirement will be smaller. So I hope you must be able to follow this lecture. Okay. So if you have any further doubt, you let me know with your comments. Okay. In the coming lecture, I will be discussing for a few more topics. Okay. So please stay connected with this channel for more updates. So thank you for watching this video. If you have any query, let me know with your comments. Thank you.